Well, hello everybody. Welcome to Blue Marble Science. Here we go again with airplanes flying over the curvature of the Earth. This time with no end of arithmetic failures involved. This is by Flat Earth Banjo. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors way back out of punching range, and let's light a dumpster fire and have some fun.
Yes, absolutely. Number one, there is a rate of descent. A rate of descent, and we can all imagine. These are simple concepts, and I'd like to reiterate that in all of my technical discussion, in any of our technical discussion, it needs go further than, meaning it doesn't, we need no more complexity than 10th grade science. 10th grade math, Pythagorean theorem, 10th grade physics, 10th grade chemistry, basic chemistry. This is chemistry 101, college level, 10th grade chemistry at the high school level. One can imagine if an aircraft is flying at elevation 35,000 feet, well, it has to descend to land on the ground. Well, it's still flying in the air. It's not going to point its nose straight down and go straight to the ground. No, it's got to gradually descend from altitude down to zero.
I guess you know that zero is mean sea level. So unless you're going to an airport that's right on the coastline, I don't suggest trying to descend to zero. You're probably going to hit a really big old spherical rock if you do.
Well, we call that rate of descent. A lot of people don't talk about this. Now, I'm bringing up a new topic to Flat Earth, and I'm really bringing up a new topic to the average pilot. The average pilot does not talk about rate of descent.
What do you mean pilots don't talk about a rate of descent? Descents are something you're going to do on pretty much every flight, unless you're planning on leaving that thing up there.
And how do I know? Because I've talked with several pilots, and they cannot quote their rate of descent. Why do I know it? Because I memorized Army federal regulated rate of descent, which was 500 feet per minute.
Did you notice your own citation says there is no regulation governing rate of descent?
For 18 years, I memorized 500 feet per minute. That's for my first 2 years as an Army aviator, I memorized 500 feet per minute is the standard rate of descent.
Oh, you're an Army aviator. Okay, this ought to be easy for you. Let's go back to your original example. I'm flying my big old jet plane from Chicago O'Hare down to Atlanta Hartsfield. I've climbed out to a cruising altitude of 35,000 feet, and I want to descend to, let's say, 5,000 feet. Here we go. Now let's do a little math. 35,000 feet minus 5,000 feet is 30,000 feet. I need to lose 30,000 feet of altitude. If I do that at 500 feet per minute, 30,000 feet divided by 500 feet per minute is 60 minutes. The entire flight lasts about an hour and 20 minutes. I would barely have time to climb to cruising altitude before I would have to begin my descent if I do it at 500 feet per minute. Don't you think it might make better sense if I selected a little bit higher number, like say 2,000 feet per minute? Then the descent phase would take 15 minutes. I could do it even faster than that if I wanted to. 500 feet per minute is a plug number that we use particularly for non-pressurized aircraft. If we descend it much faster than that in a non-pressurized airplane, it can be pretty hard on our passengers' ears. So 500 feet per minute is not necessarily the number you want to use in a pressurized airplane.
Well, that's for landing. Okay, let me reiterate. That's for landing to a full stop when the airplane wants to land to the ground and stop. That's 500 feet per minute. But we, in the flat Earth community, we know that for an airplane to fly around the globe, the supposed globe that is, there's a rate of descent associated with 8 inches per mile squared. So if we do the math, the 8 inches per mile squared at the average assuming an average airspeed of 500 miles per hour or that's really a ground speed, but it's moving through the air at 500 miles an hour. Associate that with 8 inches per mile squared. Well, the math gives us the following: 2,777 feet per minute rate of descent for that airplane to follow the globe.
Well, you might have guessed this is where he was going. You know, our atmosphere has a pressure gradient. The pressure decreases as you go up in altitude, and the air density also decreases as you go up in altitude. But at any given altitude, the density of the air is more or less constant. The lift the airplane wing produces is directly proportional to the density of the atmosphere that it's flying in. If lift is greater than the weight of the plane climbs. If weight is greater than lift, the airplane descends. But at the point in the atmosphere where lift matches weight, the airplane simply maintains its altitude. Now, if the angle of attack of the wing doesn't change, the lift doesn't change, and the altitude above mean sea level simply remains constant. That's why the airplane maintains its altitude and follows the curvature of the Earth, because the atmosphere follows the curvature of the Earth. But you know, even if what you said was true, you got the math completely wrong. You talked about an airplane flying at 500 miles per hour. That's 8.33 miles per minute. At 8 inches per mile squared, that's 8 inches times 8.33 miles squared divided by 12 inches to get it into feet, and that is 46.3 feet per minute. If our atmosphere didn't have a pressure gradient and we were actually forced to follow the curvature of the Earth, we would have to descend at the equivalent of a 46 foot per minute descent rate, not 2,800 feet per minute. You got that completely wrong. I wonder what else you can get wrong.
Okay, and that is a continuous descent, not to land. That is a continuous descent while the aircraft is at altitude flying along.
Wow.
Well, let's compare that. Let's make the comparison now. 500 feet per minute to land the airplane to a full stop at an airport. On the globe, the airplane has to descend continuously at 2,777. That's more than 5 times the rate of descent for a landing, and that's a continuous descent.
The airplane isn't descending to maintain its altitude, but 500 feet per minute works for a plane that's traveling at about a 100 knot ground speed, not for a commercial jet traveling at 175 knots. Your comparison really should have been 875 feet per minute to about 46 feet per minute, or about 1/20th, not 5 times.
So I did some more math today, by the way, Vika. Thank you for asking. It's average 500 feet per minute. Okay, so I looked up gravity, 32 feet per second squared. Okay, that's the quote supposed gravity, right? If you drop something, it in a vacuum, okay, it falls at 32 feet per second squared.
It doesn't fall at 32 feet per second squared. That is an acceleration. I don't see anything good coming from this.
Well, let's convert that to feet per minute. That is 1,920 feet per minute. Okay, that's gravity. Now, let's remember, an airplane flying around the curve of the globe at 500 miles an hour must maintain a rate of descent of 2,777 feet per minute, which is almost 1,000 more feet per minute than something falling in free fall. That's absurd. That's the most absurd measurement we could have. So I'm bringing that to the flat Earth community. That's what the math gives us, Vika, and everybody else. Can we see the perspective here? The 8 inches per mile squared around the curve of the globe at 500 miles an hour, that's faster than free fall. That's more absurd than one can imagine. Vika, that is the simple math. That's high school math right there.
What? You took 32 feet per second, multiplied times 60 seconds, and came up with 1,920 feet per second. You calculated the instantaneous velocity of a free-falling body in a vacuum after 60 seconds. The distance that body would have fallen in 60 seconds is 1/2 AT squared. That's 1/2 times 32 times 60 squared, and that's 57,600 feet. In the first minute, and only the first minute, starting with no downward velocity, the airplane, if it was falling in a vacuum, would fall 57,600 feet. And oh, by the way, the airplane reached the speed of sound after about 35 seconds. You don't have any idea what you're doing, do you?
So, I've been intrigued, and I keep taking notes as you keep talking, that there's always this new, it's not new measurements. It's not new. Rate of descent is nothing new.
Standard.
But what people seem to forget is the globe model, the heliocentric model. That science and math is never used in a functioning application.
Exactly.
Never, ever.
But you think what you just heard was math being used in a functioning manner. Just out of curiosity, what do you think dysfunctional math would look like?
Because it proves the fraud if they ever do.
Exactly. So kudos to you, and rate of descension just made my list of bullets in the gun.
That's a foundational effect of flat Earth, isn't it? It's a foundation.
Amen, brother. Amen. That and elevation angles, that and you triangulation, and I mean the list just keeps growing and growing and growing. And so Thank you. I don't want to take a lot of time here, but thank you, Rob.
Yep, and that's my point, Lon. That is exactly my point, and that's why I send out these messages to everybody in the group, so everybody can see and understand. Anybody can do this math,
and some of us can do it correctly. I don't think you're on that list.
Pilots don't know anything that's not normal. They have more experience with it, but just because they're a pilot doesn't mean they know something special.
No, we just know how to take off, fly to the other side of the planet, find the airport we were looking for, and land the thing without killing anybody. Nothing special about that.
Anybody could do this math, and anybody that does this math and can explain it, well, they're smarter in this effect than the average pilot.
Amen.
Take it and run.
Amen. So I sat in that co-pilot seat for so many times.
I'll bet the co-pilot wasn't very happy about that.
And had I known then what I know now, it just would have been a no-brainer. I know you bring a plane up to elevation.
Just a helpful tip. When pretending to be a pilot, only say the word elevation when you're talking about the runway.
To your altitude, it's locked in, and you don't bring it down until your point of destination is arrived at.
You are cleared for takeoff.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
Flight 209er, clear for vector 324.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
It's point A to point B. That's it. And there is no curvature, so all right.
Well, yeah, there is curvature, but I think you've done enough damage for one day. Hey, thanks for watching. I hope you guys enjoyed it. Don't forget those little buttons down there. And if you'd like to support the channel, patreon.com/bluemarblescience or paypal.me/bluemarblescience. I appreciate all the help you guys give me, and I will catch you on the next one.